Welcome to the module on Second Life of Electric Vehicles Batteries. In this presentation, we will examine how electric vehicle batteries can have a second life. Even after they're no longer efficient for vehicles, these batteries still have usable capacity. Reusing them in other applications helps reduce waste, cut costs, and promote a more sustainable use of resources. Electric vehicles are becoming more popular every year, as the world shifts toward cleaner transportation and lower carbon dioxide emissions. Most electric vehicles use lithium-ion batteries because of their excellent energy and power density. Typically, these batteries last about 8 to 10 years. After that, their capacity drops to around 70 to 80% of the original value, making them less suitable for demanding electric vehicle applications. As electric vehicle adoption continues to rise, we'll see a growing number of retired batteries. Instead of discarding them, these batteries can be given a second life, for example, repurposed in energy storage systems for grids or backup power. However, improper disposal poses risks of heavy metal and chemical pollution, which makes recycling and reuse essential. Developing an efficient reuse and recycling system not only minimizes environmental impact but also supports the sustainability of the electric vehicle industry as a whole. The product life cycle outlines the different stages a product goes through, from defining requirements and development to recycling at the end of its life. In product engineering, considering the entire life cycle is essential to ensure sustainability and cost efficiency. Depending on the application, variations of the life cycle model may exist. The core objective of a circular economy is to maximize the efficient use of secondary resources, making it a key principle for sustainable production and consumption. Similarly, the battery life cycle includes the primary stages of production, development, vehicle integration, usage, and end-of-life processes such as recovery and recycling. Generally, capacity loss and resistance increase are the consequence of battery aging. Battery capacity loss reduces the total amount of energy that can be stored and released, and the resistance increase will reduce the battery power capability. These two phenomena are mainly caused by the loss of lithium-ion inventory and loss of anode, cathode active materials. In addition, various working conditions may lead to different dominant aging mechanisms. The low-temperature charging and fast charging could cause lithium plating, which may lead to the loss of recyclable lithium ions. The aging trajectory changes during cycling. Usually, battery aging is close to linear in the first stage, followed by a nonlinear degradation stage with rapid capacity drop and resistance rise. The transition point between these two stages is known as the aging knee point, at which the battery operation should be stopped for safety concerns. The common definition of a battery first end of life is when the battery state of health reaches 70% to 80%. However, such a definition raises many questions about its economic benefits. It can be concluded that the operating conditions of electric vehicles will lead to different aging mechanisms inside the lithium-ion batteries. Understanding these mechanisms is critical for enabling accurate estimation and prediction of battery health. Predicting the knee point is of great significance for realizing long life service and economical reuse of lithium-ion batteries. Due to the difference between cycling profiles or electric vehicle operation and secondary energy storage, it is necessary to understand the relationship between battery aging mechanisms and working conditions. This will facilitate the fast repurposing and economical application of second life batteries. After their first use in vehicles, batteries can enter a second life through different pathways. They may be repurposed, serving in new applications such as stationary energy storage systems or backup power units. Alternatively, they can be recycled, where valuable raw materials are recovered through thermal, mechanical, or chemical processes for use in new battery production. In cases where reuse or recycling is not economically or technically viable, disposal becomes necessary to safely manage remaining components or byproducts. Choosing between repurpose, recycling, and disposal depends on the battery's condition, state of health, and economic feasibility. These strategies collectively reduce waste, conserve resources, and lower energy consumption, supporting a sustainable battery ecosystem. Repurposing retired electric vehicle batteries allows them to be given a second life in less demanding applications such as stationary energy storage systems. Because each automaker uses different battery designs and operating conditions, these batteries age differently and must go through a systematic process before reuse. The first step is collection, where retired electric vehicles are sent to authorized treatment centers. There, the batteries are carefully removed and transported to facilities capable of recycling or repurposing them. This process may be managed by the vehicle manufacturer, the battery producer, or a third-party company. Next is screening, where the condition of each battery is evaluated. Engineers assess factors like chemistry, voltage, energy capacity, and remaining useful life to determine whether the battery can be reused directly or if it needs to be dismantled into smaller modules. Advanced diagnostic and data-driven tools help estimate the state of health and predict how much longer the battery can perform safely. Finally, in the reassembly stage, suitable battery modules are grouped and reassembled based on the power and energy requirements of their new application. Cooling systems and controllers are added or modified to match performance needs. Batteries with similar aging profiles are clustered together to ensure balanced operation and reliability. Overall, this repurposing process extends the lifespan of electric vehicle batteries, reduces waste, and contributes to a more sustainable and circular energy system. Renewable energy sources like wind and solar have grown rapidly in recent years, but their energy supply is unstable and depends on weather conditions. Second-life battery energy storage systems provide a practical and affordable solution because they are flexible, scalable, and quick to respond to variations in energy supply. In remote and off-grid areas, especially in developing countries, repurposed lithium-ion batteries can be used to create small power systems, mini-grids, that provide reliable electricity. These systems are often oversized to store enough power for several days when renewable generation is low, such as during cloudy or windless periods. Operating within a moderate voltage range also helps reduce battery aging and extend system life. Second-life battery energy storage systems act as energy buffers, storing excess renewable energy and releasing it when needed. This reduces waste, lowers energy costs, and increases self-consumption of clean energy, making renewable systems more efficient and sustainable. Peak shaving, reducing electricity use during periods of high demand, is a valuable application for second-life batteries, especially in industrial and commercial settings. These systems can store energy during low-demand periods and release it when demand and electricity prices are high. While new energy storage systems can be costly, second-life batteries offer a lower-cost alternative that still provides effective demand reduction, even with reduced capacity. This makes them an economically viable option for managing energy costs. However, a cost-benefit analysis is essential to compare savings against investment costs for both new and second-life systems. Backup power systems are one of the best uses for second-life battery energy storage systems. In power plants, unexpected shutdowns, maintenance, or black start situations require a temporary energy supply to keep systems running or restart operations. Second-life battery energy storage systems provide a fast, reliable, and low-cost solution with high power output and quick response. These systems are typically used for short periods and only a few times per year. This limited use means they experience very little wear, extending their lifespan and improving cost efficiency. Beyond power plants, second-life battery energy storage systems are also used in telecommunications, data centers, and uninterruptible power supply systems to ensure continuous operation during power outages. Since these systems operate infrequently, battery aging happens mainly over time, allowing service lives of more than 20 years. Overall, applications like backup power, renewable energy integration, and demand management are ideal for second-life battery energy storage systems, offering long life, low costs, and sustainable performance. Second-life batteries have strong potential, but several key challenges limit their large-scale adoption. First, defining their place in the overall battery life cycle is complex, and extra processing adds costs that must be balanced by lower system prices. Battery availability and pricing are also uncertain. Retired batteries vary in quality, and supply often competes with the used car market. Diagnostics are another hurdle since important battery data and software are often proprietary, making evaluation difficult. There's also a mismatch between first-life and second-life requirements. Electric vehicle batteries are built for performance, while reused ones must prioritize reliability and longevity. Safety and liability standards for reused batteries are still under development, and multi-life system design remains highly complex, requiring careful integration of electrical, thermal, and mechanical factors. Addressing these issues is essential to make second-life batteries both safe and economically viable for sustainable energy use. In summary, electric vehicle adoption is growing rapidly, which means more lithium-ion batteries are reaching the end of their first life. These batteries usually last around 8 to 10 years before their capacity drops to about 70 to 80% of the original value. Battery aging occurs because of the loss of lithium inventory and active materials, leading to reduced capacity and higher resistance. This process happens in two stages: a slow, linear phase and a faster, nonlinear phase known as the knee point. When electric vehicle batteries are retired, they can be repurposed, recycled, or disposed of. The repurposing process includes collecting, testing, and reassembling the batteries for new uses. Finally, second-life battery systems are used in renewable energy support, peak shaving, and backup power applications. These uses extend battery life, lower costs, and contribute to a more sustainable energy system. Thank you for your attention.